Okay, I guess we should get going. So we have today to discuss some, unfortunately, rather formal stuff. And tomorrow we will do something that's physically more interesting, the Einstein-Podolsky-Rosen experiment, but which will draw heavily on what we're going to do today. So what we want to do today is face up to the fact that many of the systems that we want to apply quantum mechanics to come in parts. So, for example, the hydrogen atom consists of an electron and a proton, and to know the state of the hydrogen atom, you want to know the state of the electron and you want to know the state of the proton both. A diamond consists of, on the order of, so condensed matter physics is about things like diamonds, which a diamond would contain 10 to the 23 or whatever carbon atoms. And to know the state of the diamond, officially, you would need to know the state of the 10 to the 23 carbon atoms. So it's going to be important to move forward towards applying quantum mechanics to any non-trivial and really interesting system. We're going to have to learn how to describe systems that come in parts. And this turns out to be, quantum mechanics is its own way of doing this, which is actually very elegant and powerful, but leads to some surprising results. In a hydrogen atom, the electron, of course, is strongly interacting with the proton. It's electrostatically attracted towards the proton. And in a in a diamond, the carbon atoms are obviously very tightly coupled to each other by covalent bonds or whatever. So there are springs, as it were. There are things connecting the different parts. But it turns out that the quantum mechanics of a system made up of two objects is non-trivially different from the quantum mechanics of the two isolated things, even if you just logically consider them to be the same. So when we do angular momentum, we will, in the coming weeks, we will find that very strange and interesting results arise just because we put two gyroscopes in a box with no physical connection between the two of them and start asking questions about what's the angular momentum of the box as opposed to what is the case of the individual gyros. So knowing the state of the well-defined states of the box turns out to be very different from knowing well-defined states of the individual gyros. So what we're talking about today is putting things logically together to make compound systems, and there may or may not be springs physically connecting these things. All right. So the central problem of the central thing we have to address is if we have a system A and a system B, so we have two distinct systems, and this one, let's say, has states AI, right? So this indicates which system we're talking about. Then there's supposed to be a semicolon here, and there's an index here which tells us which of this system's states we're addressing. And we have a system B, and it will have states something like this. And what we want to know is, so how are we supposed to write the states of the compound system, the system that you get by considering A and B together? So this might be the electron, this might be the proton. What's the state of the compound system, which we call a hydrogen atom, for example? Right? Because if we know how to compound system A with system B to make a combined system, we can compound another one. We can use the same rule to add another element of a bigger system, A, B, C, and so on and so forth. And eventually we can build up a diamond of 10 to the 23 carbon atoms. Once you know how to add two systems, by repeating this process, adding more and more systems, you can put any number of systems together. So this is the central problem that we have to address. So the states, first of all, we just write some formal stuff. The states of the compound system AB, this is when you logically think of the system at A with B as one system, some of the states of the system AB are written like this: AB, semicolon, I, J, and we write it symbolically as A, semicolon, I, B, semicolon, J. Sorry, the semicolon and the J look too similar. So what is this? Let's just ask ourselves, what does this mean? This means the state of the compound system, where the state A, where the subsystem A is in its ith state, and the subsystem B is in its jth state, right? So this is, we have to know what this means, and I think we do know what this means. I've just given words that give meaning to that. And on the right-hand side, we have a symbolic multiplication, and we don't need to worry too much. You'll see as we go on that we don't need to worry too much about what exactly we mean by this multiplication. But this is just a symbolic product of, officially it's a tensor product, but we don't want to frighten everybody. This is a symbolic multiplication of a ket on a ket, right? We'll find out how to interpret that as we go along. Then we can have the bras. There must be associated bras. Since this is a state of a system, it has a bra, which will be is equal to, of course, the logical product of the bras. And we give meaning to this thing by explaining what happens when this goes onto this. So when this goes onto this, we should get a complex number. So to give meaning to all this, I need to explain what this is. I primed, J primed on AB, semicolon I, J is equal to, right, so we need to give, this should be a complex number. To give meaning to all this hocus pocus, I need to explain which complex number. The complex number it is this complex number, I primed AI times BJ primed BJ. So what I've written on the right is completely well defined, because this is a complex number and this is a complex number, and we can multiply complex numbers, and we get a complex number which gives meaning to this on the left. And that's really that's the essence of giving meaning to this thing here, because remember, we only want these kets. All we want with kets is in order to calculate amplitudes, whose mod squares are going to be the probabilities give us our predictions. So as long as you know how to get an amplitude out of a ket, you know enough about the ket to get on with it. Right? So we've given meaning to the process by which we extract amplitudes out of kets, which is this braing through business, because that leads to the experimental predictions, which are the whole point of the theory. Okay, why does this make sense? Why is this a sensible definition, right? So this is the definition of what we mean by these animals. Why is it a sensible definition? Well, it says that the probability of measuring the results I primed and J primed, given that we're in this state, is equal to, obviously, the mod square of this horrible thing, AB I primed J primed AB I J mod square, right? That's how we would interpret this complex number. And according to this formula, this is equal to the product of the probability associated, this is the probability for the system AB, the probability system A of getting the result I primed times the probability of getting the result J primed. Right? Because if I take the mod square of both sides, the mod square of this product is the product of the mod squares. The mod squares on this side, by definition, are these probabilities. So the probability, this says, the probability that if I take measurements on my combined system, I find that A is in the I prime state and B is in the J prime state, is simply the product of the probabilities that the A system is in the I prime state and the B system is in the J prime state if you make individual measurements. So that it makes perfect sense, and it's motivating. This is why we write the ket of the compound system like this. This multiplication rule, this symbolic multiplication, is inherited from this law for multiplying probabilities in probability theory. Now having said that, and everything's nice and simple, we have to make the point that I now want to show that not all states, this is the thing that's surprising, of AB are of the form A, B. That's what I want to now establish, that it's not true that all states of the system are of this form. Okay, so so for example, consider two-state systems. So we're going to do a concrete example to illustrate this general and very fundamental principle. We're going to have two-state systems. We're going to have A is going to have states plus and minus. These are complete set. So we're considering the simplest non-trivial example. And B is going to have the states up and down. Right? This is just notation that enables us to, by using a plus sign and a minus sign for A, and an up arrow and a down arrow for B, I avoid the necessity of writing down these pesky A, B labels, right? Let's now consider, let the state of A be A plus A minus minus. So this is a general state, okay? By taking a linear combination of the two basis vectors of my two basis states of my two-state system, I write down a general state. By choosing these amplitudes to be whatever you like, you can make any state of A whatsoever. And then let the state of B similarly be B up plus B down of down. Then, what's the state? Now let's have a look at the state AB. The state of AB that we get well, it's going to be this thing bracketed into this thing, A plus 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 A minus minus, B plus 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 B. Oops, sorry. This has the up and the down states. B subscript down, ket down. And when you multiply this out, you get a disgusting mess, right? Because you get A plus plus, A plus B down, B up of plus up plus A plus B down of plus and down plus A minus B up of minus and up plus A minus B down of minus and down. So this state is now it's now a linear combination of four states, and this is strongly suggesting that these four states are basis states for the compound system, and indeed we will show that they are, times amplitudes, which are these products of those individual amplitudes. And these amplitudes have well-defined meanings, right? So, for example, A minus B plus is the amplitude that A will be found minus and B, what did I say, up. So take the mod square of this, you get the probability of the experiment to measure A's property, and B's property will be these particular values. But what I'm trying to show is that this state is not the most general state, okay? And the way I'm going to do that is I'm going to calculate the probability that B, you should do this the same way, I've got it here, that B is up, given that A is in the plus state. Right? So this is the kind of, so if, This is a reasonable question. We've measured and found that A is up. And I now want to know, okay, so suppose I measure B's property, I found that A is plus, will I find that B's property is up or down? This is going to be the probability that given that I am where I am, B will be found to be up. Okay, well this is equal to the probability simply that we have up and the probability for being up and plus over the probability that A is plus. Now why is that? If I would move this here, then this would say that the probability of being up and plus is the probability of being plus times the probability that we get up given that we have plus. This is a very important result from statistics. This is classical probability theory. This is known as Bayes' theorem. But it's really a trivial rearrangement of the rule for multiplying probabilities. The probability to be up and plus is the probability for being plus times the probability if you are plus that you're up. So this has nothing to do with quantum mechanics. This is just a rule of probability theory, which now plays a very important role in statistical inference in all the sciences, physical and social. All right. So what is that? That's the probability that we are up and plus over having plus on A comes in. We can have plus in A in two ways with the composite system. We can have it either with B down or B up, and they're mutually exclusive events, so I can add their probabilities. So this probability on the bottom is P up plus P down plus. So what is this? This is equal to 1 over dividing through 1 plus P down plus over P up plus. What about this? Let's go back to that expression up there. What's this probability? What's this probability in terms of those amplitudes? P down plus P down, down and plus is equal to A plus B down. And P up plus, going up there, P up plus is A plus B up. So these A pluses cancel. Oh, well, we need to take the mod square of this whole thing, of course, right? But the crucial thing is those things cancel, so this is in fact equal to B down plus, this is equal to B, this ratio. So what's the point? The point is that this probability is actually, we've just shown, it's independent of A plus and A minus. So this probability does not depend on the state of A. What does that mean physically, heuristically? It means that the systems are not correlated. I've just calculated one specific conditional probability, but you could calculate any other conditional probability and you'd find the same thing, that the probability of any state of B is independent of what you assume about what the result of measuring A, and so on. These are uncorrelated systems. So what we conclude from this is that when the state of AB is a product of a state of A times a state of B, the systems are uncorrelated. And that's an important physical assumption. Now, for example, if you have a hydrogen atom, is the location of the proton correlated with the location of the electron? Well, of course it is, because if the hydrogen atom is here, you can be pretty damn certain the electron lies within a few nanometers, even within a manometer of the proton. If the proton's over here, you can be pretty sure that the electron is within a nanometer of the proton. It's over here. The electron and the proton are very strongly correlated because they're physics. There's a piece of Hamiltonian which is correlating them. So we don't, yeah. So we do expect systems to be correlated, and that means we do not expect systems in general to have wave functions that look like, to have states that look like that. So let me see. The point is that I'm not going to go through the demonstration, I think, that I said, let's go back up some way. Let's go back to here. So if these objects form a complete set of states of A and these objects form a complete set of states for B, then it's not hard to persuade yourself that these objects form a complete set for AB. All right? So this is a complete set if these complete for their respective subsystems. Now, what's this telling us? This is telling us that any state of the system, including correlated states, which, as I've tried to argue, are natural states, states in which the two subsystems are correlated, they must be writable as linear combinations of these objects. So the conclusion here is, put that back and start over here. So any state of AB can be written as AB equals the sum Cij summed over I summed over j of states A, I, B, J. These states describe uncorrelated states in which the two subsystems are uncorrelated. But this may be correlated, probably is correlated. So the way quantum mechanics introduces correlations between subsystems is by taking linear combinations of uncorrelated states. We just had such a linear combination of uncorrelated states here, right? And it turned out that in this case, that was still an uncorrelated state because this was simply an expansion in terms of some basis states of a state which was already a product of just two states. So the point is that the general state cannot be written, this thing in general cannot be written like that. Even though when you see a long list of basis states, it may, with certain complex numbers in front, it may be that the state can be written thus. So whether this thing can be written as a product of two separate states depends on these numbers. Now, we haven't got time to go into what property it is of these numbers which ensures that you can do a decomposition like this into uncorrelated states. which makes this state uncorrelated. And when these are correlated, but you can find a complete account of it in the book, there are, I think, some, and there are problems investigating this. But the point is that if you, in this concrete example here, right, this is one of the C's, this is another of the C's, another of the C's, another of the C's, and these C's are not general. They have the property, you could arrange those in a 2x2 array of objects, and if you, this matrix of this 2x2 matrix is sort of a degenerate matrix. It's a special matrix. It's not the general one that you get by choosing these numbers independently. So correlations go in like that. And in quantum mechanics, when you say that two systems are correlated, you actually usually use the word entangled. Entangled is just the same thing. It's just quantum mechanical jargon for correlated. And what it means is if a compound system or two subsystems are entangled, it means the state of the compound system cannot be written in that form. It has to be written in this form, and these numbers, these numbers do not have the property that requires them, that they have to have to enable them to be expressed as products of individual amplitudes for the individual systems. So let's do a little bit of quick counting. Suppose there are m basis states of A and n of B. All right, so there are m values that I can take, and there are n values that j can take. So then there'll be m times n amplitudes Cij. So to specify a general state of the system, you need to specify mn numbers, Cij. To specify a state, but to specify A, you need just m numbers. Ai. And to specify B, you need n amplitudes Bj. So to specify a general state of the form AB, you need m plus n amplitudes. So m plus n is generally much less than mn. If we're two, in this little example, m was 2 and n was 2, so this number was 4 and this number was 4. But supposing, so they're the same, but supposing that this number was 8 and this number was 8, then this would be 16 and that would be 64. So usually, most systems are not two-state systems. Usually, so what this is telling us is that in a general state of the system, there's very much more information than there is in here. And why is that? Because to specify a general state of the system, you have to specify all the correlations between the subsystems. And there are a lot of possible correlations. This is not a problem only for quantum mechanics. This would be a problem if we were doing statistical physics, classical statistical physics. Correlations have nothing to do, I mean, not directly to do with quantum mechanics. They're a logical problem that arises in all statistical inference, also in the classical world. And correlations are very hard to handle in classical probability theory. They're actually easier in this apparatus here because quantum mechanics pulls this amazing trick. correlated states of the system are obtained, are understood as quantum interference, right? A sum like this is a quantum interference between uncorrelated states of the system. When you're doing classical probability theory, you aren't able to pull that trick. And it's much harder to specify correlations. So correlations are important in both the classical world and the quantum world, but they're actually easier to handle in the quantum world than the classical world because of the strange way in which quantum mechanics compounds these amplitudes, does this quantum interference. So quantum interference is how quantum mechanics handles correlations, and because it has its own completely unique way of handling correlations, the results can be surprising, right? They can be ones that raise eyebrows. And the Einstein-Podolsky-Rosen experiment is an example. Let's try and pin these ideas a bit by looking at a concrete example of the H atom. So in the position representation, what do we want to know? Our complete set of amplitudes are going to be things like x, so this is let's make this the electron wave function, and we're going to have also. So we'll call this xe, therefore, and we will have xp times a big U. This will be a proton wave function, right? Which gives you the amplitude to find the proton at the point xp. This gives you the amplitude to find the electron at the point xe. And supposing these things have subscripts on them, ui and uj. So this might be the amplitude to find the electron at the point xe, given, so this might be an ui, given that the energy of the electron is ei. And this might be the amplitude to find the proton somewhere, given that the proton's energy is ej, say, right? Then what is the state? The state of the H atom would be, xp. So what is this? This is a state of the hydrogen atom in which the proton has this energy, the electron has this energy, and that gives me a state of the logically coupled pair of proton and electron. This, as I say, is not going to be a very realistic state of the hydrogen atom, because it's going to give us, this says that the electron and the proton are uncorrelated, and I've just tried to persuade you that the electron and the proton are very strongly correlated. Consequently, their wave functions this isn't going to be a realistic, useful wave function for hydrogen atoms as found in lab. So what do we have to do? A more realistic state might be xe, xp, shall we say chi, for a new label, which would be some Cij of xe ui xp big U j. But what are these? This is a boring function of x with a label I. There's a set of functions of x, e, which have labels I and return complex values. And then this complex number is multiplied on this complex number, which is a function of xp, a member of a family of functions with labels j. Here is an amplitude, another complex number. Add these complex number together, and you get this complex number. And this, so any state of a hydrogen atom must be writable like this, but realistic states are not writable like that because of this correlation of the proton and the electron. Okay, now we need to revisit collapse, of wave function. So what happens when we make measurements on compound systems? We know that when we make measurements, what happens when we make measurements on a single system, and we have to extend these ideas. So suppose, let's go back to our state of our system. So we go back to the two-state system. Two-state system. A and B. And consider this particular state. A psi which is equal to A times plus up plus minus brackets B up plus C down. Supposing this is what we have. This is pretty much written down at random. It is a well-defined state of the system because it's a sum of 3 of the 4 basis states that we were discussing, right? It's a sum of plus up, and minus down. This is the amplitude that if you would measure A and you would measure B, you'd find that A was plus and B was up. This is the amplitude for finding that A is minus and B is up, etc., etc., etc. But I've written this, but this one down. This state is, as it turns out, entangled. That is to say, you won't be able to write this as a product of a state A and a state B. So this is more realistic than the states that I was discussing before. Okay. Okay. Now suppose we measure. So let's measure. Measure state subsystem A. If we get plus, then after measurement, the theory says, right, the dogma is, I'm not going to justify this, I'm stating this as a conjecture, that the state of the system is now goes to psi primed, which is equal to plus up. So how does the system, let's just remind ourselves what collapse of wave function was all about in the one-state system, in the single system, sorry. If we had a single system, we wrote psi was equal to the sum an, let us say en, for example, and we measured E and got the answer em, then a psi went to the state m, right? After the measurement, it was in this state. So I'm making, I'm stating that in this more complicated scenario, where we have a composite system, we measure only one of the subsystems, we get a certain answer, it goes to that state, which is consistent with what we had over there, because we found the answer plus, so we threw away everything times minus, whereas over there it's simply m, the coefficient up there of plus was not just a complex number A, which was giving me the probability, it was also times this state of B. And this state of B just gets copied down. So what does this say? So this is what the theory claims, is that that goes to that. It doesn't explain how this happens. This is the problem of measurement. But there's a physical implication of this, which is that you're now a measurement of B is guaranteed to produce or to find up. Right? Because this thing is something times up, there is now 0 amplitude to find down. You're certain not to find down, you are certain to find up. Even, right. If, on the other hand, we get minus for A, then the new state is equal to the new state is equal to, yes, minus brackets B up plus C down, properly normalized, so over the square root of B squared plus C squared. So this is what the theory claims, that if you get the minus thing, then your new state is essentially the coefficient of minus and minus itself, all properly normalized. And now, so if we get minus, there is now uncertainty as to what the result of a measurement on B will be. So now measurement of B yields, for example, up with probability B squared over the square root of B squared plus C squared. So we now apply the same old rules about the probability of measuring, about the interpretation of the amplitudes, right? Because we are certain to get minus if we measure A again, but if we measure B, we can get 2 outcomes, either up or down, and the probabilities are like that. So that's a conjecture, that's a statement, a theoretical statement about how the interpretation of the theory works, and we just have to accept it and see whether it leads to proper experimental predictions. So in our last minutes, we have unfortunately a big topic to discuss, which is operators for composite systems. So we've talked exclusively so far about the kets, but we know that operators play a very important role. With every measurable quantity, there's going to be an operator, and we need to know how this behaves. So we found that the kets of the subsystems were multiplied. This rule was inherited from the multiplication of probabilities of successive events. The operators add. So for example, if we have 2 free particles, if A and B are both free particles, then HA is equal to PA squared, the momentum of A squared over twice the mass of A, and HB, the Hamiltonian operator, is equal to PB squared over 2MB. So what's the Hamiltonian of the combined system? HAB is equal to HA plus HB. In other words, it's PA squared over 2MA plus PB squared over 2MB. And that's sort of saying the energies of the combined system is the sum of the energies of the individual bits. How does the operator P, we now need to explain how an operator PA operates on one of these states here, okay? So when PA hits A, I, B, J, what we have, so this is a state of the combined system, and this is an operator which has to operate on the state of the combined system. And what does it do? It produces PA operating on AI, which is a well-defined state of A, symbolically times Bj. If PB works on this thing, PB ignores this. It passes through this as if PB was just an ordinary complex number and homes in on this, its target. So this is simply AI times PB Bj. This is a well-defined state of B, gets to be symbolically multiplied by this well-defined state of A, and there you are. So, for example, what would the expectation value AB ij of H ABB in this case here? Let's just make sure that we get some sense out of this. Sorry, AB ij. So what does that mean? That means AI J Bj brackets HA plus HB close brackets AI Bj. So this operator ignores that because it's a B operator and homes in on that. This operator operates on this, and then we have the other things come in on the other side, and this gives me HA AI Bj plus, so that comes from this, because that passes through this A operator as if this was just a number, bangs into that. Plus, correspondingly, we're going to have AI Bj HB Bj. This, of course, is going to be the number 1. This is going to be EA, the expectation value of the energy of A. This is the number 1, and this is the expectation value of B. So we find that the expectation value of the energy of the combined system is, lo and behold, the sum of the energies of the individual bits. I think that makes physical sense. It makes physical sense when the Hamiltonian takes that simple form if it's just the sum of the individual bits. But for example, for hydrogen, the Hamiltonian H is equal to P electron squared over 2 mass of electron plus P proton squared over 2 the mass of a proton minus the charge on the electron squared over 4 pi epsilon naught x electron minus x proton in modulus. All right, because the energy of the hydrogen atom is the sum of the kinetic energy of the electron and the kinetic energy of the proton and an interaction energy of the two. Right, because they electrostatically attract each other. So this is equal to H electron plus H proton, these being the Hamiltonians of the free electron and the free proton, plus an interaction Hamiltonian. And the thing about this interaction Hamiltonian is that it depends on operators belonging both to the first subsystem and the second subsystem. And the consequence of that is that HE, H interaction, commutator, is not equal to naught because the PE, the electron momentum operator sitting inside here, has a bone to pick with the electron position sitting inside here. And similarly, of course, HP, H interaction is not equal to 0. So without that interaction, we would have that the... So what's the important point about this is that the Hamiltonian of the hydrogen atom does not commute with the Hamiltonians of the electron and the proton. You cannot know the energy, so generically you do not expect to be able to know the energy of the hydrogen atom if you know the energy of the electron, because they don't commute. And it's the interaction that stops them computing. Well, we're going to have to stop, unfortunately, at that point. But we're pretty nearly done. I'll just write down one final statement, which is that the operators of different subsystems always commute. Right. So, for example, p proton, comma, x electron is precisely nothing, etc. We do not have to worry about non-vanishing commutators of operators that belong to different subsystems. Okay.